Hey everyone, it's Horizon of the Universe. In today's video, we're diving deep into the Big Bang Theory. The Big Bang Theory suggests that the universe began expanding from a super-dense singularity. But don't get it twisted. This bang isn't an explosion in the way we normally think about one. It marks the birth of space-time and all the laws of physics. In the very first moment, 10 to the power of -43 seconds, during what's known as Planck time, quantum gravity effects ruled the show. At this stage, the universe sprang into existence from a quantum foam, and its temperature soared to 10 to the power of 32 Kelvin. In the first minutes after the bang, as the temperature dropped, the quark-gluon plasma transformed into hadrons, protons, and neutrons. By the third minute, nucleosynthesis kicked in. Protons and neutrons combined to form deuterium, helium, and a tiny bit of lithium nuclei. Believe it or not, about 25% of the helium we see in the universe today was cooked up during that very period. Then, 380,000 years later, the universe became transparent as electrons finally bonded with atomic nuclei. The leftover radiation from that time is what we now call the cosmic microwave background, discovered back in 1965 by Arno Penzias and Robert Wilson. The temperature of the CMB, which is around -270 degrees Celsius, that is roughly 2.7 Kelvin, along with its amazingly uniform distribution, stands as one of the strongest pieces of evidence for the Big Bang. Later on, satellites like WMAP and Planck measured tiny fluctuations in the CMB, revealing the very first seeds of galaxy clusters. Back in the early 20th century, people thought the universe was static and infinite. In 1917, Einstein even added a cosmological constant to his general relativity equations in an effort to keep the universe static. But then, in 1922, Alexander Friedmann showed that the equations naturally pointed to a universe that was either expanding or contracting. In 1927, Georges Lemaitre built on Friedmann's solutions and proposed that space itself was expanding. He even calculated how fast galaxies were receding. Of course, back then his ideas were met with criticism for being way out of the ordinary, almost like they were too detached from conventional philosophical thinking. Then came 1929. When Hubble used a 2.5-meter telescope at the Mount Wilson Observatory to analyze spectroscopic data from 46 galaxies, including Andromeda. The redshift in the light coming from these galaxies was explained by the Doppler effect. Turns out, galaxies are moving away from us. On top of that, Hubble's law, where velocity equals h0 times distance, showed that the faster a galaxy moves away, the farther it is from us. This finding made Einstein's once-introduced cosmological constant, what he later called his biggest blunder, seem completely unnecessary. Hubble's constant tells us the current expansion rate of the universe. Yet today, there's a bit of a debate. two different methods for measuring this rate give slightly different values. For nearby galaxies, we use Cepheid stars, whose brightness cycles help us gauge distances, and then we calibrate Type E supernovae, our standard candles, to measure the distances to galaxies that are much farther away. Now, the reason galaxies seem to be moving apart is because the fabric of space itself is expanding, a phenomenon known as metric expansion, which is defined by Einstein's field equations. What's really interesting is that local gravitational systems, like galaxy clusters, aren't affected by this cosmic stretching. For instance, while Andromeda is actually heading toward the Milky Way because of their mutual gravity, most other galaxies are speeding away from us. As light travels from distant galaxies, its wavelength gets stretched out by the expansion of space, causing it to shift towards the red end of the spectrum. This effect is measured by the formula Z equals delta lambda over lambda naught. For example, if a galaxy has a Z value equal to 1, it means that the universe has expanded to twice its size since the light left that galaxy. Then, in 1998, observations of Type Ia supernovae shocked the scientific community by showing that the universe's expansion is speeding up. This totally unexpected discovery gave birth to the concept of dark energy. So, what exactly is dark energy? Einstein's lambda term in his equations might represent the energy stemming from quantum fluctuations in the vacuum. But here's the kicker. Quantum field theory predicts an energy density that's 10 to the power of 120 times larger than what we observe. This mind-boggling discrepancy is famously known as the cosmological constant problem. Some theories suggest that dark energy might actually be a time-varying scalar field, what's often called quintessence, while others propose modified gravity theories, such as F of R gravity, which tweak the rules of general relativity. Projects like DSI, the Dark Energy Spectroscopic Instrument, are being designed to put these models to the test. The observable universe spans a diameter of about 93 billion light-years, which is way more than what you'd expect from the distance light could travel in roughly 13.8 billion years at its constant speed. This apparent contradiction is explained by the theory of inflation. In a ridiculously brief period, from 10 to the power of negative 36 seconds to 10 to the power of negative 32 seconds after the bang, the universe expanded by an unimaginable factor. Inflation, first proposed by Alan Guth in 1980, accounts for the remarkable uniformity and flatness of the universe. In fact, during that fleeting 10 to the power of negative 36 second interval, the universe is believed to have expanded by a factor of 10 to the power of 26. One of the pieces of evidence for inflation is the detection of B-mode polarization in the cosmic microwave background. Measurements indicate that the overall geometry of the universe is Euclidean, which supports the idea of endless expansion. Still, there are also some wild speculative theories out there, like models suggesting the existence of a multiverse. So, what's in store for the future of the universe? Will it expand forever, or is a dramatic end in store? Scientists have come up with two major scenarios: heat death and the Big Rip. Both of these possibilities paint a pretty dramatic picture of what might eventually happen. If the universe's expansion continues at the pace driven by dark energy, eventually every galaxy will drift further and further apart. Star formation will grind to a halt, and the universe will gradually cool down until it reaches a state of complete inactivity. This eventual fate is what we call heat death, or the Big Freeze. But how exactly does that process unfold? First, the stars we see will gradually die out as they burn through their nuclear fuel. Some will fade into white dwarfs, others may collapse into neutron stars or even black holes. Next, galaxies will start to crumble as they lose most of their material due to gravity, leaving behind only dark matter and the remnants of dead stars. Then, according to Stephen Hawking's theory, black holes will slowly evaporate over incredibly long time spans thanks to Hawking radiation. Once that process is complete, there won't be any significant exchange of matter or energy left in the universe. Finally, as the universe reaches thermodynamic equilibrium, its temperature will approach negative 273.15 degrees Celsius. That is, absolute zero. At this point, no chemical or physical processes can take place, and the universe will have reached a completely dead state. In short, according to this scenario, the ultimate fate of the universe is to become an endless, dark, and frozen void. On the other hand, the Big Rip is a scenario that might occur if the universe's expansion accelerates without any brakes. In this case, dark energy would grow stronger over time, eventually ripping apart the very fabric of the universe. The key here is the value of dark energy's equation of state parameter, often denoted as W. If this parameter falls below -1, then dark energy wouldn't just push the universe apart. It would start tearing apart matter itself, right down to the atomic level. So, how does the Big Rip actually go down? First, the gravitational pull between galaxies weakens, causing each galaxy to become isolated from the rest of the universe. As the expansion speeds up, planets and stars begin to drift apart, and even our own solar system won't be spared. Planets like Earth would start disintegrating as the forces that normally hold them together are overcome by the rapid expansion. In the final stages, the expansion becomes so extreme that it tears electrons away from atomic nuclei and even splits protons and neutrons into their constituent quarks. So, how does the Big Rip actually go down. First, the gravitational pull between galaxies weakens, causing each galaxy to become isolated from the rest of the universe. As the expansion speeds up, planets and stars begin to drift apart, and even our own solar system won't be spared. Planets like Earth would start disintegrating as the forces that normally hold them together are overcome by the rapid expansion. In the final stages, the expansion becomes so extreme that it tears electrons away from atomic nuclei and even splits protons and neutrons into their constituent quarks. Ultimately, the universe would be completely torn apart by this boundless, energy-driven expansion. Some scientists estimate that if dark energy truly follows the Big Rip scenario, this catastrophic event could occur in about 22 billion years. So, which scenario seems more likely? Current observations show that the universe's expansion is indeed accelerating, but we still don't fully understand how dark energy behaves over time. If dark energy remains constant, then heat death appears to be the more likely outcome. However, if dark energy grows stronger as time goes on, then the Big Rip might be on the cards. For now, the data we have leans toward heat death being the more probable fate, although we'll need many more observations before we can say anything for sure about the future of the cosmos. In the end, the destiny of the universe remains one of the biggest mysteries out there. No matter which scenario ends up being true, one thing is certain: the universe will never remain in the form we know it today. With ongoing and future observations, scientists hope to inch ever closer to unraveling this colossal enigma.